lecture, I argued how the solutions of the wave equation for electromagnetic potentials can be written in retarded form. That is, given a source which is composed of charges and currents varying with time, I could write that the vector potential A r at t is given as mu naught over 4 pi integration d tau prime, where tau prime indicates the volume integral, j r prime at time t minus r prime over c divided by r minus r prime, and the scalar potential phi r t equals 1 over 4 pi epsilon 0 integration d tau prime rho r prime at time t minus r prime over c divided by r minus r prime, and this whole thing calculated at retarded time is sometimes also indicated as j r prime t prime retarded, and similarly here this thing is indicated as rho r prime t prime retarded. And then one can calculate the electric and magnetic fields from these as E r t equals minus grad of phi minus dA dt, and B r t as curl of A. I obtained these expressions by arguing how, starting from a source, the potential propagates with a finite speed c. Now, what I want to do in this lecture is give mathematical derivation of the same expressions. And for this, I am going to use Green's function technique. I am after the solution of these equations. Which are of the generic form. These two, all these equations, 4 of them, can be written as del square some function f of r and t minus 1 over c square d 2 f over dt square equals some function g r t. This is an inhomogeneous equation. So, the general solution is a combination of f homogeneous plus f particular. F homogeneous is the solution of this equation with right hand side being 0. So, f homogeneous satisfies the equation f homogeneous minus 1 over c square d 2 f by dt square equals 0. So, this can be mixed with the particular solution for a given source, and what we are after in this lecture is that particular solution d 2 f r t minus 1 over c square d 2 f by dt square equals g r t. And the Green's function technique for this is, if I can solve the same equation with right hand side being delta function. So, I am solving for del square G r r prime t t prime minus 1 over c square double derivative with respect to time of G r r prime t t prime equals delta r minus r prime delta t minus t prime, putting a minus sign, so that takes care of the minus sign in the wave equation. Then the general solution, let us also put a minus sign here in the wave equation. In the wave equation there is a minus sign. Then the general solution f r t will be given as integration G r t r prime t prime G r prime t prime d tau prime d t prime, which is quite easy to see, because if I apply this operator del square minus 1 over c square d 2 by dt square on G, it gives me the delta function, and that delta function integrated with G gives me f. So, let us see if this really gives me that solution. So, I am taking the Green's function to be that function that satisfies del square G r t r prime t prime minus 1 over c square d 2 g over dt square equals minus delta r minus r prime delta t minus t prime. I switch between r prime and d t prime. So, just bear that with me. And I am claiming that then the solution of del square f r t minus 1 over c square d 2 f by dt square equals g r t, the minus sign in front is nothing but integration G r t r prime t prime G r prime t prime d tau prime d t prime. This will be f r t. To show this, let us apply del square minus 1 over c square d 2 by dt square on f. This on the right side will give me integration. The same operator I can take inside the integration, because this depends on unprimed variables g r prime t prime d tau prime d t prime, and this is nothing but minus integration delta r minus r prime delta t minus t prime g r prime t prime d tau prime d t prime, and this gives you equals minus g r t. So, if I can find that Green's function, I am done. So, let us see what this Green's function looks like. So, I am after del square G r t r prime t prime minus 1 over c square d 2 g over d t square equals minus delta r minus r prime delta t minus t prime. We will take care of time dependence and space dependence one by one. What this essentially means is that I am solving, right. This essentially means what we are doing is, let us just understand that. What we are doing is, we are writing solutions for particular frequencies omega, and then superposing them. And you will see how it is done. So, let me keep writing this equation that we are solving. Del square g minus 1 over c square d2g dt square equals minus delta r minus r prime delta t minus t prime. I am going to write delta t minus t prime as 1 over 2 pi integration e raised to minus I omega t minus t prime d omega, and then solve for one particular frequency. So, let us write del square g minus 1 over c square d2 g over dt square equals minus delta r minus r prime e raised to minus I omega t minus t prime. I will solve for this particular omega, and then I can add it all up to get my final Green's function. And let me put omega here. So, I am looking for one component of omega. Final g r t r prime t prime is going to be equal to integration whatever this function g r r prime is e raised to minus I omega t minus t prime d omega 1 over 2 pi. So, I am right now considering only one component part of it, this frequency omega dependent part. I can also write here omega. Since I am considering this omega part, what I have is this g omega r r prime e raised to minus I omega t minus t prime is the component that I am after, and I am going to substitute this in the equation. When I do that, I get del square g r r prime, this is for a particular frequency omega, minus 1 over c square times omega square with a minus sign. So, that will become plus g omega r r prime equals minus delta r minus r prime. Write k equals omega over c. To write this equation as del square plus k square g omega r r prime equals minus delta r minus r prime. This is our good old Helmholtz equation. That I talked about in the previous lecture also. You have seen the solution of equations with delta function on the right hand side. You have seen the solution of potential for a point charge which has a delta function density. The only new thing out here is this k square on the right. So, I leave it for you to show that here G w r r prime comes out to be e raised to I k modulus of r minus r prime over 4 pi mod r minus r prime. Show that the solution above satisfies a Helmholtz equation. Once we have that, then I can write that solution of this g minus 1 over c square d 2 g over dt square equals minus delta r minus r prime e raised to minus I omega t minus t prime, and there was a 2 pi also here, is g omega r prime equals 1 over 4 pi e raised to I k modulus r minus r prime over r minus r prime times e raised to minus I omega t minus t prime over 2 pi. Keep in mind that k is omega over c. So, my general g r t r prime t prime is equal to 1 over 4 pi integration 1 over 2 pi e raised to I k modulus r minus r prime over r minus r prime e raised to minus I omega t minus t prime d omega, which I can write as 1 over 4 pi I will leave out, mod r minus r prime I can take out, because that does not depend on omega, and I have inside 1 over 2 pi integration of e raised to I omega over c r minus r prime e raised to minus I omega t minus t prime d omega, which is equal to 1 over 4 pi modulus r minus r prime 1 over 2 pi integration e raised to minus I omega t minus t prime minus r minus r prime over c d omega. And this, by definition, is the delta function, and therefore, this whole thing comes out to be 1 over 4 pi 1 over modulus r minus r prime delta of t prime minus t minus mod r minus r prime over c. This is my Green's function. So, what we have found is that if I were to solve this equation, minus g r t, I write the corresponding Green's function equation as del square of g r t r prime t prime minus 1 over c square d 2 g r t r prime t prime over d t square equals minus delta r minus r prime delta t minus t prime, and then write my solution f r t as integration g r t r prime t prime g r prime t prime d tau prime d t prime, and the corresponding Green's function that we found from solving this equation comes out to be g r t r prime t prime as 1 over 4 pi modulus of r minus r prime times delta function of t prime minus t minus mod r minus r prime over c. And therefore, the solution f r t is equal to 1 over 4 pi integration G r prime t prime times delta t prime minus t minus mod r minus r prime over c d tau prime dt prime, which is 1 over 4 divided by, there is a divided by also, divided by r minus r prime. So, this is 1 over 4 pi integration d tau prime g r prime t prime retarded divided by r minus r prime. And this is exactly the solution that we had proposed. So, we have now derived it in a rigorous mathematical manner. So, to conclude this lecture, we have shown through Green's function technique that the solutions of the wave equation are given by retarded solutions. We will use these to calculate the corresponding electric and magnetic fields and the Poynting vectors and the radiation in coming lectures. Thank you.